Thanks, Greg. And if we could get my first slide up. That's not it. Here we go. Okay, very good. Thanks again, Greg. Appreciate the invitation to talk about this exciting mission concept that my collaborators and I have been working on for the better part of a year. It's exciting because it is a combination of human and robotic exploration, science and human exploration that will take us to new places that neither humans nor robots have been to before. As Greg alluded to, it's a mission of human astronauts aboard the Orion spacecraft that will go to the L2 Lagrange point that sits above the lunar far side. And this mission will be done in conjunction with a robotic spacecraft, a lander and a rover on the far side that will be teleoperated by astronauts aboard the Orion spacecraft. So it's an opportunity to advance both human exploration as well as science, and it will, as I will explain in a few minutes, hit two of the priorities from two separate decadal surveys, from the planetary sciences and from the astrophysics decadal surveys. My partners in crime are shown here. Let me single out David Kring, who is our resident lunar geologist and has set me straight on the exciting lunar science to be done with this particular mission. So David is down in front here that if I make any mistakes, you're going to jump up and correct me right in real time, right, David? And Scott Norris and Josh Hopkins from Lockheed Martin. Lockheed Martin is part of our lunar team and has been from the very beginning, and we really appreciate their collaboration. Joe Lazio and Justin Casper, also from our lunar team. So, the lunar far side. Why are we interested in the lunar far side? There's been lots of discussion here about that. Brad Jolla, for example, was talking just this morning, and the focus group also about South Pole Lake and Basin. Of course, we know, this group knows almost without saying, that it is virtually a whole new unexplored world with a surface area greater than the continent of Africa, totally unexplored. We've not been to the surface either with robots or with humans. And very importantly, it's right in our backyard. It's relatively easy and nearby to get to. This particular mission is one that will help us to, I think our laser pointer is getting weak here, but it'll help us to with the kind of teleoperation that we're talking about here, to demonstrate human robotic exploration techniques that will be needed not only to explore the moon, but in future asteroids and Mars. So it'll advance those exploration goals. And as, again, this community knows in particular, the far side is dramatically different than the near side. We still don't really understand why. Among the features, of course, you have much more highland regions on the far side. Only about 1% of the far side is occupied by lunar maria versus nearly a third of, thank you, Yvonne, nearly a third of the near side. So, I mean, basic questions about why, what happened in the evolution of the moon that produced such a difference between those two. And very importantly, as I mentioned before, The far side includes the South Pole Lake and Basin. You can see this on this LRO high-resolution map. Your laser pointer is dying too. I think it is. I think I'm shorting everything out here today. So you can see in this darkened region up over here the impression, which is the South Pole Lake and Basin, which is possibly the largest, deepest, and oldest impact basin in the inner solar system, and a critical area to bring samples back according to the last 2 Planetary Sciences Decadal Survey. And also because the moon is tidally locked, the far side is always facing away from the Earth, which means it also has a very valuable characteristic for us astrophysicists, namely it's the one place in the inner solar system that's known to be radio quiet. It's pristine in this direction. It's the one place that we know that we will be able to pursue observations of the very early universe, the epoch of first stars and galaxies called cosmic dawn, that I'll talk more about as well. That too is a priority of the one of the decadals, the astrophysics decadal in this case. So here's the mission concept, at least part of it anyway. What I'm showing here are the Lagrange points in the Earth-Moon system. The 5 Lagrange points, these are equipotential gravitational surfaces that you're seeing here. L2 sits at about 65,000, thank you, about 65,000 kilometers. Let's see if I can make this one die as well. 65,000 kilometers above the far side. That would mean that human beings at L2 will be further by 15% away from the Earth than they've ever been before. And so that's a step in the right direction. Also, this is relatively easy to get to in terms of the delta V in fuel that's necessary. The idea is that the Orion spacecraft, which is, as we heard the other day, a funded program by NASA, the Orion spacecraft would be launched by the SLS, which is also underdeveloped in a funded program, carrying up to 4 astronauts. You can see the escape tower over here. This would be the rocket motor for the translunar injection, and this would go to L2. One of the reasons we're excited by this is because this mission is far less expensive than an Apollo-style sortie mission. We all know that anytime we want to try to put human beings onto and lift them off of a still relatively deep gravitational potential well like the moon, it's very expensive. This mission is affordable within NASA's current and notional out-year budgets, which of course is very important in the climate that we're living with today. And also the timetable for this would allow this mission to take place by roughly the end of the decade. Preceding the launch of the astronauts, we anticipate that we would put down an unmanned lander and a rover on the surface that would both collect vital samples from this region of the South Pole Lake and Basin and also deploy our low-frequency radio telescope. So a little bit more about those things later, but that's the combination of the two. Here's a little video that Lockheed Martin has put together that shows in brief form the mission concept, launch from Earth, a gravitational assist, a slingshot around the moon, which helps greatly in terms of the fuel and cost. The spacecraft then would go into a halo orbit around L2 such that it would be both visible, the Earth would be visible, and so would the far side. Potentially a space station module, maybe provided by the Russians, would fly and be placed there as well and dock with Orion, allowing longer missions. The astronauts aboard the Orion would be in direct communication with the rover on the far side. And because the delay time is only 0.3 of a second round trip, you could have real-time joystick control of the rovers, such as what you see here in this simulation. Of course, the astronauts probably not dressed up nearly as well as what you see here, but that's all right. The return mission after possibly a couple months would once again be a gravitational slingshot around the moon, then a return back to the Earth, and a splashdown in the Pacific Ocean. Okay, where do we want to go? Well, this is where David Kring has guided us among a number of interesting features that one could go within the South Pole Aitken Basin is the Schrodinger Crater. What you're looking at here, of course, is a LOLA topo map, and you see in purple this depression in the lunar surface, which is the South Pole Aitken Basin. And then this crater off to one edge is Schrodinger. As David has pointed out to us, it's the second youngest impact crater, but it lies within the oldest impact basin on the moon. And that has some real advantage. And here is an LRO image of the Schrodinger crater. This upwelled material here is the result of the impactor that created the Schrodinger, and having drawn up material from an already excavated region as a result of the original South Pole Aitken Basin impact. This subsurface material comes from layers that are quite deep and primordial and ancient, and these rocks that are right up here are quite old, as expected. So that with a rover, one could pick up these very ancient materials and bring those back for further study on the Earth for geological investigation. We've also investigated this basin because it is fairly near the limb of the moon to see how radio quiet it is. My postdoc, Abidata, has run a electromagnetic simulation that includes the overall features of the moon and the particular features of this crater. And we've been able to determine that it should have a shielding of about 80 dB or greater, which means that it's quiet enough for the kind of cosmological observations that we're talking about doing here with very weak signals. All right, a little bit more about the science goals, and I'll show in the background, having run this very nice LRO movie that folks at Goddard have prepared, very stylized and idealized, but showing the creation of the South Pole Aitken Basin back about 4.3 billion years ago, followed by several 100 million years later, this impacts for the so-called late heavy bombardment epoch, that was responsible for creating the majority of the basins on the moon. So the reason I play this is because it illustrates the highest priority science mission, the highest priority from the decadal recommendation about the moon, and that is to test the lunar cataclysmic hypothesis. As I said, it was the top priority of both the Planetary Sciences Decadal and also the previous NRC report on the scientific context for exploration of the moon. In a nutshell, we would like to be able to determine the age of these oldest impact basin forming event on the moon. That will be an anchor then to understanding the beginning of this basin forming epoch, and also provide critical data on the flux of the impactors, which, particularly at the late heavy bombardment, may have resulted from this major rearrangement of the giant planets, which according to the NICE model took place at about the same time. At about that time, we had a gravitational resonance between Jupiter and Saturn that resulted in an outward migration of those two giant planets, again according to this model, and an inward migration of a whole host of asteroids and impactors. And further work on this model and verifying this model through collecting samples here would be a key. The other reason this is interesting and fascinating is, of course, this is about the same time that life was beginning to form on the Earth. Could those asteroids have brought biogenic materials to the Earth, and or at least with the impactor stirred the pot of already existing biogenic materials through the heating of the surface, the atmosphere, the proto-oceans at that period of time, and be linked to the origin and evolution of life. These are really big questions, really big, basic, fundamental questions that missions like this can offer, and the kind of things that, once again, Brad Jolliffe has been, with his Moonrise mission, talking about for years. The surface operation, we're talking about having a very modest rover because we're going to be just focused on sample collection. The teleoperation, though, I'll just remind ourselves once again, of a rover like this from L2 is going to be key in future exploration of the Moon, asteroids, and Mars. The Orion crew would implement a traverse sequence that would be predetermined by lunar geologists, but then adapted in real time as this mission is executed. Collection of samples, very importantly documenting those samples, and modest instrumentation, probably most importantly a high-resolution camera and a mechanical arm that would go along with this, and then return those samples to the lander and an ascent vehicle. One of the, I think, kind of neat things would be to have that sample rendezvous with the returning astronauts, so that the astronauts show up back at Earth, never having actually put boots on the ground on the far side, but they're carrying a bag of the oldest rocks ever to be studied. For PR purposes, that would certainly be kind of an interesting way of making this whole thing work, and also show the synergy between humans and geological science. In addition, we're also proposing to deploy our low-frequency Polymide film antennas. This is a technology a number of you have heard folks like Joe Lazio and myself talking to you all about for years and years, because we have developed this technology consisting of these thin Polymide films covered with deposited with a metal conductor that would serve as either a single antenna, like what you see here in a test we did recently in the desert of New Mexico, or a number of encoded dipoles on there in which we could phase it up as an imaging array for the future. Here you see a cartoon of it being deployed, for example, by a rover on the far side. We have tested at great length the Polymide film in a vacuum chamber at the University of Colorado. One of my students, Laura Kruger, is here, has been very much involved for a number of years in this testing. You see this video inside the vacuum chamber. This is a copper-coated Polymide film. We have built a little mini rover inside the chamber, which we teleoperate it from outside, deploy it. This gets thermally cycled to the conditions between the day and night of the Moon, and back and forth a number of cycles. Also, we have a UV lamp inside so that it gets exposed to the kind of solar radiation that is similar. And this material has held up very well in our laboratory testing. So it's a good candidate for operation at low frequencies. So why do we want a low frequency antenna on the far side? Well, for one thing, as I mentioned before, it's radio quiet, but the science that we want to do is something that was identified by the astrophysics decadal called cosmic dawn. That's the epoch of the first stars and galaxies. Here's a cartoon picture of the evolution of the whole universe. One picture, isn't that nice? Big Bang up over here, and we've got today's universe down below. It's a logarithmic scale in time. Just a couple of features that I want to identify, because what we're trying to probe is a currently unexplored part of the universe, literally the first billion years of the universe. We have some data up over here at about 300,000 or 400,000 years after the Big Bang, called the cosmic microwave background. So spacecraft such as WMAP and Planck have been exploring this era, but it only samples one narrow part of time. On the other end, after roughly a billion years or so, we have these beautiful images from telescopes like the Hubble Space Telescope. This is the Hubble Ultra Deep Field, and it shows that we have a universe that is all ionized, that is ionized gas between the galaxies. How do we get from here to here? Well, we have very little structure to a universe that is filled with structure. And this is where a lot of the action is taking place. Coming out of the CMB era, this is where the first atoms are formed, so where the first electrons and protons are coming together to form hydrogen. And so you have an all-neutral hydrogen intergalactic medium. But within that are the seeds of the first stars and galaxies. They begin collapsing under their own gravity with dark matter seeds, actually, to spur them on. and they go through their lifetime very quickly after they form stars, explode as supernovae, and produce these hot bubbles of ionized gas that you see as these kind of fuzzy yellow blobs. As more of these turn on, you begin illuminating the universe. That's the cosmic dawn that I've been talking about. And as more of these turn on, they begin overlapping these hot bubbles, and eventually this results, according to theory, the reionization of the universe. Now, what I just described is all theory. We have no data. And the reason we have no data is this era in the dark ages and the cosmic dawn, this is before the first normal sources of radiation that we use to probe the universe have formed, namely stars and galaxies. So you can't use the Hubble Space Telescope. You can't use the James Webb Space Telescope. We can't use the ALMA ground-based telescope. But in this epoch, there is hydrogen, as I mentioned before, and at these redshifts, at these distances and time periods, hydrogen emits low-frequency radio radiation, below 100 megahertz. And my theoretical colleagues have made some concrete predictions about signals that we should see in a global spectrum. This is a sky average spectrum. Think of this as power versus frequency. And these features that appear in the spectrum correspond to when the first stars turn on, when the first quasars or black holes turn on, and when the reionization of the universe begins. Very fundamental, basic information which we can extract from a dipole antenna on the lunar far side. So this is the cosmic dawn, and it was one of the 3 top science priorities of the astrophysics decadal, and they characterized it by 2 questions in the decadal. What were the first objects to light up the universe, and when did they do it? So that's what's addressable by this low-frequency antenna on the far side. But this Polymide rollout antenna can also be used for other things as well, including planetary science. And just my colleagues, led by Justin Casper in his postdoc, have studied the use of these antennas to measure nanodust, which, traveling at hundreds of kilometers per second, part of the solar wind, may be a key source of weathering of airless bodies, like the moon, like asteroids. And they have verified this technique recently using the stereo spacecraft, in which a fast nanodust particle strikes the spacecraft, produces an ionized clouds, and those electrons then migrate to the antenna and produce a signal or a flash, if you will, in the detector. They have studied this in detail and have found that the cumulative flux, for example, is very nicely correlated with mass. And so with such an antenna, you can measure the mass distribution of impacts of nanodust. So extrapolating this now, and this paper, by the way, has been published in Geophysical Research, this discovery paper, extrapolating this now to our rollout antenna on the surface of the moon with, say, a total surface area of 1,500 square meters, that is expected to yield 1,500 impacts per second of nanodust. And so this could be, as I said, a powerful probe of a component of weathering that we currently don't have a very good handle on. The other thing that we could do, and again, my apologies why these slides are dim, but we can also use this for measuring the lunar ionosphere. And this too, as we've heard from a number of talks throughout the last few days, is a recommendation from the Planetary Sciences Decadal to understand the origin and evolution of these thin planetary exospheres that occur on so-called airless bodies. The way we do this with a radio detector is that the galaxy is a very strong source of low-frequency radio emission, so that galaxy emission is coming through this thin exosphere on the moon, and with the radio telescope on the surface, you sweep through the frequencies. As you get to the low frequency end, you're going to get a sharp cutoff that corresponds to the plasma frequency. And the nice thing is that plasma frequency is very simply related to the square root of the density of the ionosphere. So you've got a relatively simple way of probing it. This technique, by the way, is called rheometry, and it's used commonly on the Earth to probe the ionosphere. There's a lot about the ionosphere, its variability, its relationship to bursts of activity from the sun are not well determined at all, and so this is a key area that potentially could be probed. We are going to make a first test of this telerobotics idea this next summer, utilizing several collaborators here at Ames, Terry Fong and Maria Bualat at NASA Ames, coupled with my student Laura Kruger, Joe Lazio, and myself, are going to use the K-10 rover and astronauts aboard the International Space Station to test the deployment of Polymide film. The idea is to, we are building this summer a deployment device to be outfitted on the K-10 rover. And the idea is to have the astronauts teleoperate the rover, possibly on the Ames Marsscape, if it's still here next summer, but some location at NASA Ames. Have them teleoperate it, deploy the Polymide film, so test the techniques and technologies associated with that, and unroll the Polymide film, and then we'll embed some flaws in it and have the astronauts attempt to determine those flaws and come up with a remediation program to deal with that. So this will be a stepping stone in the direction of that. This is a program that is funded by the Office of the Chief Technologist right now. I think that's right, Maria, isn't it? And so we are moving forward with that, and we're this summer in the design stage, the mission concept planning phase. So to summarize and conclude, what's exciting about this mission is the extraordinary number of firsts that could be conducted by this mission. It would be the first to investigate the surface of the far side of the moon. It would be the first to bring back samples of the oldest impact basin in the solar system, which, as I've said several times, is a priority of the planetary sciences decadal. This mission also would allow us to deploy for the first time our novel Polymide film radio frequency antennas on the far side, and then, therefore, it could be the first to actually make a detection or an exploration of this unexplored epoch of the universe, namely the cosmic dawn, the first stars and first galaxies. And this mission would be the first to demonstrate teleoperation of rovers by astronauts at a Lagrange point, and therefore it would be a pioneering step in the kind of exploration strategies that are thought to be necessary for early missions to asteroids and Mars. So, Greg, with that, I think I'll stop. Thanks.
Thanks very much, Jack.
And thanks for the help with all the laser pointers here.
Gone through 3 of them now. So, questions, Yvonne?
Yeah, Jack, I thought I remembered that the radio astronomers actually have some concern with us polluting the radio space by having an L2 presence with humans. Is that true, or am I just making that up?
It is, and so that's one of the issues that's of concern. But if we're careful in how we operate, for example, our radio communications being at a much higher frequency, and we're careful with the communications devices so they don't bleed over, then this is eminently controllable, so that the astronauts in the Orion capsule will effectively have a Faraday cage within the Orion capsule. That should not be an issue, but it continues to be one that we monitor very carefully. So you are right. It's very easy to pollute ourselves. We've done that on the ground of the Earth. The combination of the RFI plus the ionosphere is what is driving us to the moon to begin with.
Other questions? Dan.
Jack, if I missed this, I was looking down, and when you were talking about your upcoming demo in 2013 using the K-10, what about the possibility of using the ISS as the equivalent of L2 with the astronauts controlling your rover, K-10 rover from the ISS, admittedly not, you'd have to LOS, AOS it, but I know the ISS has a lot of experiments that are related to their iStar experiment, which is looking at all of the operational considerations and physical considerations associated with remote control of a surface body from an orbiting body. That might be a good match.
Maria, any comments on that? You're more of an expert on this than I am.
Sorry. We did go through iStar. We originally were going to be sponsored by them, but then the Technology Demonstration Office decided that they